Imagine tunnels stretching deep beneath rivers, bridges rising over 200 meters into the sky, and highways spanning kilometers to connect bustling cities. These aren't just structures, they're the backbone of America's future. In 2024, the United States is tackling some of the most ambitious infrastructure projects ever attempted, with costs reaching into the billions and engineering feats pushing the limits of technology. From massive steel frameworks and reinforced concrete foundations to high-speed rail systems and intricate highway interchanges, these mega projects are reshaping the nation's landscape and economy. How are these projects overcoming incredible technical challenges to redefine the future of American infrastructure? All right. Let's talk about one of the biggest and boldest transportation projects in the United States, the California High-Speed Rail. This is about building a super-fast train system that connects the major cities of the state. Think of it like this: a train that zips from San Francisco in the north down to Los Angeles in the south and even further to cities like San Diego. It's all about speed, comfort, and cutting down travel times. The idea started back in 2008. California voters approved funding for this high-speed rail because they wanted a faster, cleaner, and better way to travel across the state. Right now, driving from San Francisco to Los Angeles takes at least 6 hours, and flying might seem quick, but it comes with long waits at the airport. This train would change all that. You'd hop on in San Francisco and arrive in Los Angeles in less than 3 hours. And because it's electric, it's much better for the environment than cars or planes. Now, the original plan aimed to connect major cities while also stopping at smaller towns along the way, giving more people access to this new system. But like any big dream, it's had its share of challenges. Costs have gone way up, from an original estimate of $33 billion to now over $128 billion, and the timeline has stretched. Instead of being ready by 2020, as originally planned, we're now looking at some parts being done in the 2030s and beyond. But here's the good news: the project is moving forward. The most progress so far is in a region called the Central Valley, which is sort of the middle part of California. Picture the area between San Francisco and Los Angeles. Right now, crews are building a 191-kilometer stretch of the rail here, passing through places like Madera, Fresno, Kings, Tulare, and Kern counties. If you're looking at a map, that's the area roughly halfway between the Pacific Coast and the Sierra Nevada mountains. It's the agricultural heart of California, with wide open spaces that are perfect for building the first section of the high-speed rail. This section will eventually connect Merced, a city to the north of the Central Valley, with Bakersfield, a city to the south. When this 275-kilometer stretch is complete, it'll serve as the backbone of the high-speed rail. The first trains will run here, and testing is expected to start as soon as 2028. Now, let's zoom in and talk about what's being built. To make the train line work, engineers are building some amazing structures. One of the most impressive is the Hanford Viaduct, a long bridge-like structure that lets the train cross over obstacles like roads and rivers. This viaduct is made of 740 giant concrete beams, called girders. Each girder weighs several tons and stretches dozens of meters long. When finished, the viaduct will be over 1 kilometer long, allowing the train to speed through the area without interruption. Nearby, there's another major structure called the Tulare River Viaduct. This one uses 264 concrete girders and has special beams on top for extra support. When you look at it on a map, this viaduct will sit right in the heart of the Central Valley, connecting towns and cities in the region. Let's keep moving south. Another cool feature is the Deer Creek Viaduct. This structure will stretch about 900 meters and is already taking shape, with 33 of its planned 43 support columns finished. Columns are those tall concrete posts you see holding up bridges. They're reinforced with steel and designed to be super strong so the train can pass over them at high speeds safely. The engineers are also working on something called grade separations. If you're wondering what that means, it's where the train line goes over or under roads instead of crossing them. This is important because it makes the rail system faster and safer. One example is the Belmont Avenue grade separation near Fresno. Workers have already installed 14 of the 28 concrete girders needed for the bridge there. These girders are massive. They're over 45 meters long and weigh more than 84 metric tons each. Once finished, this structure will let cars and pedestrians move freely underneath the rail tracks. Another grade separation is happening near Madera at Road 26. This one will carry cars and people over both the freight tracks and the future high-speed rail line. At 19 meters tall, it's an impressive sight, and crews are almost done building the columns and horizontal supports. Now, let's talk about the stations. In the Central Valley, stations are being designed for cities like Fresno, Bakersfield, Hanford, and Merced. These stations aren't just places to hop on and off the train, they're being planned as hubs for the community. Imagine modern buildings with shops, restaurants, and easy access to other forms of transportation. Teams are using 3D models to show local communities what the stations will look like, and they're gathering feedback to make sure they fit the needs of each area. Testing for the first trains is expected to begin in 2028, starting with the Central Valley section. These trains will be state-of-the-art, designed for speeds of up to 350 kilometers per hour. Imagine zipping across California at that speed. They'll also be super efficient, with electric power and a sleek design. Beyond the Central Valley, crews are already preparing for the next steps. They've completed environmental reviews for 680 kilometers of the planned route, including segments between Palmdale and Burbank in Southern California. That's the stretch that brings the train closer to Los Angeles. Clearing these sections means they can start construction soon, bringing us closer to connecting the state from north to south. So, moving to another groundbreaking project, let's talk about the massive effort to transform semiconductor manufacturing in the United States. This is a big one. It's not just about making more computer chips, it's about reshaping an entire industry that powers everything from your smartphone to the most advanced military hardware. The US used to lead the world in making semiconductors, but over time, most of the production shifted to Asia. Now, with huge investments and state-of-the-art technology, America is making a comeback. The key player here is Intel, which is expanding its operations across several states, including Arizona, New Mexico, Ohio, and Oregon. These aren't just factories, they're called fabs in the semiconductor world, and they're engineering marvels. Building one of these fabs takes about 5 years, 6,000 workers, and costs close to $10 billion. Just think about that. These aren't your typical buildings. Each fab is a giant, high-tech fortress with multiple levels, all designed to work together like a finely tuned machine. Let me walk you through what goes into building one of these fabs, and we'll use Arizona as our starting point. Intel is currently building 2 new fabs there, each costing between $15 billion and $20 billion. These will be some of the most advanced semiconductor plants in the world. These fabs will support growing demand for chips used in artificial intelligence, 5G networks, and supercomputers. To give you an idea of scale, just the foundations require removing over 1 million cubic meters of soil and rock. That's like filling 400 Olympic-sized swimming pools. After that, they pour 600,000 cubic meters of concrete, which is twice as much as was used to build the Burj Khalifa in Dubai. Once the building takes shape, it gets packed with high-tech equipment. Each fab holds 1,200 tools that turn silicon wafers, flat disks about the size of a pizza, into hundreds of tiny chips. These tools are so sensitive that even a single speck of dust could ruin a chip. That's why the chips are made in clean rooms, which are areas with filtered air and precise temperature and humidity controls. The clean room takes up the second level of the fab, and the equipment to support it, pumps, transformers, and pipes, sits below it on the sub-fab level. Above the clean room is the fan deck, which keeps the air particle-free. This setup makes sure everything runs smoothly. Moving east to Ohio, Intel is doing something even bigger. They're calling it the Silicon Heartland, and it's the largest private sector investment in the state's history. Near Columbus, Intel is building 2 brand new fabs at a cost of over 18 billion euros. This isn't just about making chips, it's about creating an entire tech ecosystem in the region. The site will employ 3,000 new Intel workers and support 7,000 construction jobs. Let's shift now to New Mexico, where Intel is upgrading 2 existing fabs near Albuquerque. These fabs are being transformed into advanced packaging facilities. Packaging might not sound exciting, but it's actually one of the most innovative parts of chip making right now. Intel's new packaging technology allows multiple chips to be stacked together, improving performance while reducing costs. This is especially important for applications like artificial intelligence and 5G networks, where speed and efficiency are everything. To make it happen, Intel is investing 3.2 billion euros and adding 700 new jobs in the area. Heading west to Oregon, Intel is expanding its research and development hub near Portland. This site is where the next generation of semiconductors will be developed. They're investing billions here to keep the U.S. at the forefront of chip technology. Oregon's fabs already employ over 22,000 people, and the expansion will add thousands more. If you've ever wondered where the cutting-edge ideas in semiconductors come from, it's places like this. Now, let's zoom out and talk about the big picture. Why is the U.S. putting so much effort into chips? It's because semiconductors are essential for everything, from smartphones to national security. Right now, the US makes only about 10% of the world's chips. Most of the advanced ones are made in Taiwan, which creates a huge risk for supply chains. That's where the CHIPS Act comes in. This federal program provides 36 billion euros in funding to companies like Intel to build fabs and bring semiconductor manufacturing back to the US. Let's not forget the engineering feats behind these fabs. Each one uses 35,000 tons of structural steel. That's 5 times the weight of the Eiffel Tower. They also install over 9 million cubic meters of cable, enough to stretch through 214 marathons. And the chillers that cool the equipment? Each one weighs 50,000 kilograms, as much as 12 African elephants. These fabs are a mix of brute strength and incredible precision, all working together to produce chips smaller than a grain of rice. Now, moving on to another marvel in progress, let's explore the Gordie Howe International Bridge. This is no ordinary bridge. It's set to be the longest cable-stayed bridge in North America and a game changer for trade and travel between Detroit, Michigan and Windsor, Ontario. Picture a massive structure spanning 2.5 kilometers, linking 2 countries across the Detroit River. This project is about connection, efficiency, and engineering brilliance. Construction on this bridge began back in 2018, but the story dates much further back. For years, the Ambassador Bridge was the main crossing between the US and Canada in this area, handling about 25% of all US-Canada trade. While impressive, it has its limits. Traffic congestion, aging infrastructure, and a lack of direct highway connections on the Canadian side caused delays, making the need for a new bridge clear. That's where the Gordie Howe Bridge comes in. So, what makes this bridge so special? Let's start with the design. The Gordie Howe International Bridge is a cable-stayed bridge, which means it uses strong steel cables to hold up the road deck, supported by 2 massive A-shaped towers on either side of the river. These 2 towers are each 220 meters tall. That's taller than most skyscrapers, and they anchor 216 steel cables. The main span, the part of the bridge that hangs between the towers, stretches 853 meters, making it the longest of its kind in North America. The bridge deck is wide, with 6 lanes for vehicles, 3 going in each direction, and a separate path for pedestrians and cyclists. This path will connect to trails and bike lanes on both sides of the border, making it the first legal pedestrian crossing over the Detroit River. At its highest point, the bridge will rise 46 meters above the water, ensuring plenty of clearance for the large ships that navigate this busy waterway. Let's talk about the ports of entry. These are massive facilities at both ends of the bridge, where customs and border checks will happen. On the Canadian side, near Windsor, the port of entry covers 53 hectares, while the U.S. port near Detroit is even larger, at 68 hectares. That's equivalent to over 120 football fields combined. These facilities are being designed with state-of-the-art technology to handle up to 26,500 vehicles a day by 2025, up from the current 18,500. Dedicated ramps will connect the bridge directly to Interstate 75 in Michigan and Highway 401 in Ontario, ensuring smooth traffic flow. Now, let's dive into the construction. Building something of this scale isn't easy. The first step was clearing and preparing the land, which involved relocating utilities and contaminated soil. Next came the foundations for the towers. These are massive underground structures made from reinforced concrete, designed to support the weight of the bridge and withstand the forces of wind and water. Over 7,600 cubic meters of concrete were poured just for the tower footings. The towers themselves required innovative techniques. Their A-shaped design meant they had to be built with a slight curve, called a camber, to counteract the forces pulling them inward. Temporary crossbeams were added during construction to stabilize the structure until the cables were installed. By late 2023, both towers had reached their full height of 220 meters, and crews began installing the steel cables. Each cable is made from high-strength steel and is designed to last over 125 years. Another engineering challenge was the road deck. To protect against corrosion in the industrial environment near the Detroit River, the steel deck is coated with a special 3-layer paint designed to last over 40 years. Each deck section was lifted into place using massive cranes, and by mid-2024, the two sides of the bridge were permanently connected. The bridge is also designed with sustainability in mind. Green spaces are being added around the ports of entry, and the project includes 20 million euros worth of community benefits for neighborhoods near the bridge. These include park improvements, noise barriers, and grants for local community groups. For example, in Detroit's Delray neighborhood, residents can choose to have their homes renovated or relocate to new homes in other areas. The Gordie Howe International Bridge isn't just a marvel of engineering, it's a symbol of international cooperation. Funded by Canada, the €6.4 billion project is being repaid through bridge tolls. Despite delays caused by the COVID-19 pandemic, construction is progressing steadily, with the bridge deck expected to be completed by the end of 2024 and the full structure ready for vehicles by the fall of 2025. From spanning international borders to seamlessly connecting bustling roadways in Texas, it's amazing how engineering can reshape the way we move. Now, let's dive into the DFW Connector, a project that's revolutionizing the flow of traffic around one of the busiest airports in the world, the Dallas-Fort Worth International Airport. While it doesn't tower over rivers, it weaves its own story of technical precision and innovative design over a sprawling 13.5-kilometer stretch of highway. The DFW Connector is more than just a highway expansion. It's a carefully orchestrated transformation of State Highways 114 and 121, turning what was once a congestion nightmare into a state-of-the-art road network. Picture this, a project so ambitious, it involved more than 1.2 million metric tons of concrete, enough to build over 400 Olympic-sized swimming pools, and over 35,000 metric tons of steel, about 5 times the weight of the Eiffel Tower. Let's break down some of the technical achievements. The initial phase, completed in 2014, involved doubling the road capacity with new main lines, improved frontage roads, and cutting-edge Texpress lanes. These express lanes are dynamic, adjusting toll rates based on real-time traffic to give drivers a faster, smoother option when needed. It's like having a VIP lane during rush hour. But the work didn't stop there. In 2016, engineers tackled FM 2499, a vital corridor connecting SH 121 to Denton Creek. This part of the project involved digging below-grade main lines, essentially creating tunnels that let traffic bypass busy intersections at Grapevine Mills Boulevard and Stars and Stripes Way. Excavating over 600,000 cubic meters of soil, enough to fill 240 Olympic pools, was no small feat. This design not only sped up traffic, but also reduced noise for nearby communities. Another technical highlight came with the ramps leading from SH-121 to SH-360, which opened in record time in November 2015, a full year ahead of schedule. The challenge here was balancing heavy construction while keeping the existing traffic moving. Crews managed this by prefabricating key components, such as girders and beams, and assembling them on site. These ramps now handle thousands of vehicles daily, seamlessly guiding them onto major routes. One of the crowning achievements came later with the improvements to the interchange that connects SH-114, SH-121, and SH-26. This was a tangle of high-volume roads where every second of delay rippled through the region. Engineers designed new direct connectors that streamlined traffic patterns and cut down on bottlenecks. With over 9 kilometers of new roadway added, this portion of the project was delivered 6 months early in 2021, underscoring the team's commitment to efficiency. Let's not forget about the technology behind the scenes. Modern drainage systems were installed to handle Texas's sudden storms. These systems included massive culverts and underground channels, capable of diverting millions of liters of water away from the roads, keeping them safe during heavy rains. Advanced traffic management systems, including sensors and cameras, were also embedded into the infrastructure to monitor and respond to congestion in real time. Aesthetics and sustainability weren't overlooked either. Every bridge and overpass features a consistent red and beige color scheme with detailed Texas star motifs on the column caps, giving the entire corridor a sense of regional pride. Noise barriers with textured stone designs were added in residential areas to reduce traffic sound while blending seamlessly into the surroundings. Construction teams also adopted a design-build approach where design and construction happened simultaneously. This method allowed crews to start building finished sections of the highway while others were still being planned. For example, as design teams finalized the layout for SH-121, crews were already paving sections of FM 2499. This overlapping process saved years of construction time. And it wasn't just the roads themselves that benefited from this transformation. The project team worked closely with local businesses and residents to minimize disruption. One innovative solution was setting up temporary access roads for businesses affected by the construction. These roads kept customer access flowing while crews worked just meters away. The DFW connector also set benchmarks in sustainability. Recycling programs ensured that materials like concrete and asphalt were reused whenever possible, reducing waste. Solar-powered lights were installed along key stretches, cutting down on energy use. Today, the DFW connector has become a symbol of what smart infrastructure can achieve. It's not just about moving cars from point A to point B, it's about making that journey safer, faster, and more reliable. With smoother traffic flow, reduced emissions, and improved access to one of the busiest airports in the world, the benefits of this project extend far beyond the roads themselves. The Gateway program is one of the most ambitious infrastructure projects in the United States, aimed at revolutionizing the aging and critical rail system along the Northeast Corridor. This massive effort includes the construction of new tunnels, replacement of deteriorating bridges, and upgrades to stations and tracks, all designed to support modern train systems and increasing passenger loads. At the heart of the Gateway program is the Hudson River Tunnel project. The existing North River tunnels, built in 1910, are over a century old and struggling to handle the 450 trains and approximately 200,000 passengers that pass through daily. These tunnels are in a precarious state, with water damage from Hurricane Sandy in 2012 accelerating the deterioration of their concrete linings, electrical systems, and tracks. Engineers needed a solution that would both restore the old tunnels and keep trains running without major disruptions, leading to the plan for a brand new tunnel system under the Hudson River. The new Hudson River Tunnel will be a twin-tube system running approximately 4 kilometers long, each tube containing a single track. Together, they will provide the redundancy needed to allow rehabilitation of the old tunnels without halting service. Excavation will be performed using advanced tunnel boring machines, TBMs, each capable of cutting through up to 15 meters of soil and rock per day. The TBMs will bore through layers of soft clay, sand, and rock beneath the Hudson River, and the entire operation will require precise control to avoid destabilizing the riverbed or interfering with existing underground utilities. Each tube will have an internal diameter of 8 meters, lined with reinforced concrete segments. The concrete must meet rigorous standards to resist water pressure, chemical corrosion, and long-term wear, ensuring the tunnel can remain operational for at least 100 years. Specialized grout will be injected between the concrete lining and the surrounding soil to seal the structure and stabilize the ground. Ventilation and drainage systems will be installed within the tunnel to manage water infiltration and air quality, critical for passenger safety. Once the tunnel is operational, work will begin on rehabilitating the North River tunnels. This process will involve removing the old concrete linings, cleaning and reinforcing the steel structures, and replacing outdated electrical systems with modern alternatives. Crews will also replace tracks, ballast, and signal systems to meet current standards. These upgrades will increase train speeds and reduce delays caused by outdated infrastructure. On the New Jersey side of the river, several projects are tied to the Gateway program. The Portal Bridge Replacement Project is particularly noteworthy. The existing Portal Bridge, a swing bridge over the Hackensack River, has long been a bottleneck for rail traffic due to frequent malfunctions. This 113-year-old structure is being replaced with 2 fixed-span bridges, each 15 meters high. The first new bridge, costing 1.8 billion euros, began construction in 2022 and is scheduled for completion in 2027. This design allows trains to pass at speeds of up to 160 kilometers per hour, compared to the current bridge's limit of 60 kilometers per hour. The second bridge, planned for future construction, will provide additional capacity to accommodate growing rail traffic. Further upgrades include replacing the sawtooth bridges near Secaucus, New Jersey. These bridges, also over a century old, are essential for connecting multiple rail lines. The new structures, estimated to cost 2 billion euros, will feature wider tracks and stronger materials, enabling higher train speeds and reducing maintenance requirements. Work on these bridges is set to begin in 2024. To handle increased passenger and train volumes, Secaucus Junction, officially known as the Frank Lautenberg Transportation Center, is being expanded. This 1.8 billion euro project will add platforms and tracks to accommodate more trains, including direct services to Manhattan through the planned Bergen Loop. The Bergen Loop, another 1.3 billion euro project, will create a new rail alignment, eliminating the need for passengers from certain New Jersey lines to transfer at Secaucus Junction. On the New York side, extensive work is underway to prepare for the new tunnel's arrival. Crews are constructing a massive concrete casing beneath Hudson Yards, where the tunnel will connect to Penn Station. This casing, built using reinforced concrete, will act as a protective shell for the tracks and systems passing through one of Manhattan's most densely developed areas. The Gateway program also includes a significant overhaul of New York Penn Station, the busiest rail hub in the U.S. Engineers are working on a 7 billion euro redesign that will expand the station's footprint, improve passenger flow, and modernize facilities. Plans call for 23,000 square meters of open space, with additional platforms, escalators, and elevators to enhance accessibility. Natural light will be introduced through skylights and glass-paneled entrances, creating a brighter and more welcoming environment. The station will also receive upgraded track and signal systems to accommodate the increased train traffic expected once the Hudson River Tunnel and other projects are completed. Currently, the station's tracks and platforms, built in 1910, can handle about 1,000 train movements per day. The upgrades aim to increase this capacity by 20%, supporting faster and more reliable services. The overall cost of the Gateway program is estimated at 16 billion euros, making it one of the largest public works projects in U.S. history. By 2035, the new Hudson River Tunnel is expected to be fully operational, and the rehabilitation of the North River tunnels will be completed by 2038. These projects, combined with the replacement of aging bridges and the expansion of stations, will transform the Northeast Corridor into a modern, efficient rail system. For the first time in over a century, the U.S. will have a rail network capable of meeting the demands of 21st century transportation. That wraps up our deep dive into one of the most critical infrastructure projects in the United States. Don't forget to like, subscribe, and turn notifications on.